Okay, so we did the integral balance for mass. Let's do the same thing for energy. It's going to be very similar to what we did for the mass balance. So again, starting point statement, rate of accumulation of energy within the control volume plus net rate at which energy leaves is equal to Q dot minus W dot, right? And we saw from the derivation of the energy balance in MEB2 that your work term is composed of multiple parts, two of which you dealt with, the flow work and the shaft work. Okay, so now let's see, how do you evaluate the different terms now? Let's go term by term. The first is to evaluate the net rate at which energy leaves the control volume. So fluid comes in, fluid goes out, it cuts across the surface, and flowing fluids carry energy. So the idea is you take a small area dA, you compute the rate at which energy cuts across that surface dA, and then you integrate it over the full control surface, you get the net rate at which energy leaves. So again, this is the same vector notation slide that you saw in the mass balance video, and which we try to explain in the vector notation video. So I'm not going to look into that right now. But again, I think there's one point worth emphasizing here. The energy flow rate, so you pick a small area dA, the mass flow rate times energy per unit mass gives you the rate at which energy flows through that area, right? So this is your m dot, that is nothing but kg per second. E has units of joules per kg. So when you multiply both, you get joules per second, or the rate at which energy flows through surface area dA. So very simple. Now what is E composed of? E composed of potential energy per unit mass, Gy, kinetic energy per unit mass, V squared over 2, and the internal energy per unit mass due to its thermal state, right? Higher the temperature, higher the internal energy. So E is composed of these three terms, right? So please keep this in mind. Units, E is what? Energy per unit mass, or in SI units is joules per kg. Okay, so again, I'm not going to talk about this again. So rho times V dot N dA gives you the mass flow rate. Mass flow rate through an area dA. Mass flow rate times energy per unit mass gives you the rate at which energy leaves, flows across the surface. You evaluate this integral over the full control surface. You're going to get the net rate of transport of energy across the surface of the control volume, right? So very simple, nothing complicated here. So we have evaluated one term. Now what is rate of accumulation of energy within the control volume? So rho times dV gives you the mass inside the control volume. Mass inside, mass of a small volume dV is rho times dV gives you the mass. Now mass times energy per unit mass gives you the energy present in that small volume dV, integrated over the full control volume, and how that is changing with time gives you the rate of accumulation of energy within the control volume, right? So again, rho times dV gives you mass. Mass times energy per unit mass gives you the energy inside a small volume dV, integrated over the full control volume. That's why you have three integrals, because it's volume now. And how that is changing with time gives you the rate of accumulation of energy. So we have evaluated the left hand side, which says the net rate at which energy leaves plus rate of accumulation of energy is equal to Q dot minus W dot. So what is Q dot, what is W dot? Again, it's the same thing. The rate of addition of heat to the control volume from its surroundings, right? And W dot is rate of work done by the control volume on its surroundings. Again, keep in mind the notation, the sign convention is going to be very important. And as we saw in the derivation, right? Even in for mass and energy balance too. So let's take it term by term. What is W dot? W dot is the rate of work done by the control volume on its surroundings. There are typically a number of work types that are to be included in this expression. First is shaft work, which causes a shaft to rotate or accomplish the raising of a weight through a distance. That's just the definition of work, right? Shaft work, suppose you have a pump. In a pump, you're pumping energy into the system and trying to move it from one place to another. You have a stirrer, in which you're pumping in energy to stir the contents of a vessel. Or shaft work can also be a turbine, right? But in a turbine, it's the fluid that does work on the system, on the surroundings. So shaft work is external work. Flow work. So again, the flow work. Where does flow work come in, right? Suppose, we saw this again in the derivation before, where at the entrance, say, to the control volume, it's the surroundings that has to do work on the system so that it can come into the system, while on the exit, it's a system that does work on the surroundings for it to go out, right? So usually it consists of pressure, and there may be some viscous effects as well. For discussion of this, please refer to your textbook. So the idea is the work done on the surroundings to overcome normal stresses on the control surface where there is fluid flow. So that's why you have flow work. There's another work, shear work, but in a lot of instances, the 3 is negligible compared to 1 and 2. So in a number of cases, it's neglected. It's a work performed on surroundings to overcome shear stresses at the control surface. So obviously there's friction, you're trying to flow the fluid past the solid surface. So there is going to be some viscous dissipation effects, unrecoverable energy. It cannot be used to recover the mechanical energy, and which is what is the shear work, right? Tau is a shear stress. We're going to see this quite a bit in transport 2 as well. So the total work W dot is composed of Ws dot, this is the flow work, and this is the shear work. Okay, so again, the W dot is composed of shaft work, flow work, and this is the shear work. Again, how do you determine the flow work? Look at this. It's a very simple expression. Pressure times area is force. Force times velocity is rate of doing work. Basic physics, right? Pressure times area is force. Force times velocity is rate of doing work. So that is your flow work. So this is the flow work. As the fluid flows through a small area dA, you integrate it over the full control surface, you're going to get the total flow work, right? And again, V dot n, there's a -1 at the inlet and +1 at the exit, right? So that takes care of whether the fluid is coming in, and when the fluid is coming in, the surroundings do work on the system, while when the fluid is going out, it's the system that does work on the surroundings, right? So the V dot n takes care of that. Again, coming back to your full energy balance, the net rate at which energy leaves the control volume plus rate of accumulation of energy in the control volume is equal to Q dot minus W dot. The W dot is composed of 3 terms, shaft work, flow work, and the shear work. So when you take the flow work over to the left hand side, what you're going to see is you have you can work out the math. You take the flow work over to the left hand side. You have E plus P over rho, and E is composed of Gy V squared over 2 plus U. And when you take U plus P over rho is nothing but your enthalpy per unit mass, right? And that is your standard expression that you see in MEB2, where what do you have? You have m dot times delta H cap plus delta V squared over 2 plus G times delta Z is equal to Q dot minus Ws dot. This might be the expression that you're used to seeing in mass and energy balance too, where obviously in deriving this expression you have chosen it to be at steady state, right? If it is at steady state, dou by dou t of this term is going to go to 0. So again, this integral expression, it's just an easier way of writing things. Hopefully you'll get used to it as we go along. And this is going to be the starting point for a number of problems that we're going to solve in energy balance, right? So please, if you can, memorize this equation. This is going to be very important. Okay, again, the standard definition, E plus P over rho, Gy plus V squared over 2 plus U plus P over rho. U plus P over rho is your enthalpy per unit mass, right? And again, E has units of joules per kg. Okay, so again, standard definition, sign convention, Q dot, rate of heat transfer, positive if heat is added to the system, negative if heat is removed from the system. Extremely important, keep this in mind. Shaft work, rate at which the system does work on the surroundings. Positive work is done by the system, negative the work is done on the system, right? Again, important, keep this in mind. So here is just a simple case. Let's say this is directly from a textbook. This is a vessel, say a box, right? There's a pipe that comes into the box, fluid can come in, and there is a pipe that is attached to the exit of the box, so fluid can go out. So fluid comes in at section 1, fluid leaves at section 2. At the section 1, the components are V1, A1, rho 1. At section 2, the velocity is V2, the cross-sectional area is A2. I think so. I think the density is rho 2, right? Okay. And again, there is a WS dot and there is a Q dot. WS dot is a shaft work. Q dot is the rate at which heat comes in. Energy balance, net rate at which energy leaves, and let's say I've included, I'm talking in terms of enthalpy right now, so that's why I have the PP over rho here. Rate of accumulation of energy is equal to, and this term, the shear work, is going to be 0 in most cases, negligible compared to Q dot and to the rest of the terms. And this is your Q dot, this is your shaft work. So again, net rate at which energy leaves, again talking in terms of enthalpy, because you have E plus P over rho, is nothing but this is your exit. So this is the rate at which energy leaves, this is the rate at which energy comes in. So exit minus inlet gives you the net rate at which energy leaves, right? I mean, rho 2 V2 A2 gives you your m dot. M dot times energy per unit mass gives you the rate at which energy leaves. This is your m dot. Energy per unit mass gives the rate at which energy comes in. Okay, so I think that is clear. So now how does my energy balance simplify? Again, energy per unit mass, m dot, energy per unit mass, m dot at inlet is equal to, this should be Q dot minus WS dot, Q dot or Q. You can rearrange terms, and then you get to this simple expression for the energy balance, right? Which is what you have seen before. I mean, you can write it in a number of different ways if you want. I mean, you can also, I think a lot of people are used to say in the Bernoulli's energy balance and things like that. So basically, you can start out from the basic energy balance. You can keep on simplifying terms, and you can get your expression for your Bernoulli's, right? We will do that later on. But again, I hope you're going to see this expression being used in a number of problems as well. So again, just like in the mass balance, the starting point is always definition of the energy balance. Look at it term by term. The net rate at which energy leaves, you can talk in terms of enthalpy plus rate of accumulation of energy equal to Q dot minus WS dot, where WS dot is your shaft work now. And that is a starting point. Start from there. You can solve a number of problems using the basic energy balance. And you can also come up with simplifying assumptions, and then which will lead you to the Bernoulli's expression, the mechanical energy balance, and so on. So then we're going to use that in a number of problems in this particular, in this case. So